In another video, we looked at the idea of exponential change, and that idea came from a differential equation that looked like this, where the rate of change is proportional to the value of the function itself, and we ended up with an equation that looked like this, where the value of something, or the size of something, is equal to the initial value times e to the kt, where k is what we call a growth constant, and that k depends on several things. It depends on initial conditions and how fast something is growing. We're going to use this equation and apply it to a few different things. We're going to apply it to compounded interest on an investment. We're going to apply it to radioactive decay, and we're going to apply it to the cooling of an object. The first application we'll look at here of this exponential growth is compounded interest on an investment. We can modify that equation to fit this particular application. The only change here really is that we replaced the k with an r. The r here is the interest rate. Since t is measured in years, then r would be an annual interest rate. We could also look at time in months if we had a monthly interest rate. And this particular equation is the equation we get when the interest is compounded continuously. We'll also see examples on investments where the interest is not compounded continuously, but it might be compounded daily or monthly or yearly, and in that case this equation would not apply. One particular example here, we'll say that we're going to invest $1,000 in an investment that accrues interest at a rate of 3.1% annually, and that's compounded continuously. And we want to know how many months it's going to take for our investment to double. This doubling question is a common one with investments. We call this doubling. It's kind of obvious why, I think. And so we want to know how long it's going to take our investment to double. Since our investment's going to double here, we're going to start with an initial condition of $1,000. It's going to double, so we're going to end up with an investment of $2,000. And so we get this equation here. To solve for t then, which is going to be the amount of time it takes to double, we divide both sides by 1,000, and we can simplify this left side here. 2,000 divided by 1,000 is simply 2. And this is interesting here because this equation actually doesn't depend on the amount that we started with or the amount we finished with, but it just tells us that this is how long it's going to take to double. So we would end up with the same answer here, whether we are doubling $1 or $1,000 or $1 million or really any amount. To solve for t here, we'll take the natural log of both sides and then divide by the interest rate, 0.031. And since t is measured in time and our interest rate was an annual interest rate, we get this many years. However, the question asks for how many months it's going to take to double, so we'll multiply this answer by 12. And we're going to get this many months. And using a calculator, we get about 268 months. Usually we would round our answer to the nearest thousandth. In this case, the way the question is asked, it would be appropriate to round to the nearest month. Another application of exponential growth is actually exponential decay. In this case, the amount of something is not getting larger, but it's getting smaller. In this example, we're replacing the k with a negative k, and we'll keep k positive, but since it's the opposite of k, then what we're going to see here is the amount getting smaller instead of bigger. One example of this is something called carbon dating. There are a lot more intricacies than we see in this problem here, but this is a basic carbon dating problem. In carbon dating, we use the fact that there's carbon-14 and carbon-12 in the environment, and carbon-14 is radioactive, and it decays into carbon-12. So if we know the amount of carbon-14 and carbon-12 that an object starts with, or at least the proportions, and we know what they end with, then we should be able to tell how old the object is. It does take about 5,730 years for half of carbon-14 to reduce to carbon-12. This number is called the half-life. Half-life is just the length of time that it takes one element to decay into another, a radioactive element to decay into another. And so we can use this idea of the half-life to figure out what the growth constant is going to be for carbon-14 and figure out what K is. So to set this up here, since 50% remains after 5,730 years, we will use 50 for our final value and 100 for our initial value, since we have 50 parts per 100 parts initially remaining. And then we'll use this to solve for K by dividing both sides by 100. We can reduce this fraction if we want. It's not totally necessary, although it makes this problem a little easier because we can write this as 2 to the negative 1 when we take the natural log of both sides, and that allows us to get rid of our negatives. Without doing this, we would end up with the same answer still. To get K by itself, now we simply divide by 5,730, and K is equal to the natural log of 2 divided by 5,730. Now that we know what the growth constant is for carbon-14 decaying into carbon-12, we can use that for our particular thingamajig that we would like to date. Since this particular thingamajig has 70% of its carbon-14 remaining, we'll say that 70 is our final value and 100 was our initial value. And we do the same thing here, but we solve for T now. We'll take the natural log of both sides. We'll divide by this number right here on both sides. And then we plug it into our calculator, and we get an answer of 2,948.504 years. So our thingamajig is almost 3,000 years old. There is a margin of error here, and if you'd like to read more about that, it's not difficult to find research on carbon dating. Since this is a process that a lot of scientists might do fairly often, we can come up with a particular formula for a half-life where we don't use e as the base, as the exponential base, but we use 1/2 as the exponential base. This equation right here is a much simpler equation to use. We wouldn't have to solve for our growth constant because the half-life is built into the equation here. That's the h. So if this is something we were going to do over and over with a particular growth function, we might simplify the growth function or apply the growth function specifically to our needs. So using this formula on the same problem, we get a setup that looks like this. And then it's just a matter of solving for T here. The solution at this point is very similar to what we had before, except we don't have e as the base. So we take natural log of both sides, and then using the exponential law of logarithms, we can take that exponent out front, and then we get T by itself by multiplying by 5,730 and dividing by the natural log of 1/2. And so we end up with the exact same number of years that we got in the last problem, with a much simpler process. This process is simpler because we took the equation that we had and we applied the equation specifically to our application. We could do this with any type of growth if we were going to have the same type of problem over and over again. One last application of exponential growth, and this certainly isn't the last of all of the applications, but this is the last one we'll look at here, is called Newton's law of cooling. And Newton's law of cooling basically tells us the rate that an object will cool in an environment. And so the temperature of the object is going to equal the surrounding temperature plus this difference between the initial temperature and the surrounding temperature times e to the negative kt. And this part right here should look familiar. It's the same thing we've had in all of our exponential functions. Since the temperature is cooling, then we have a negative constant, kind of like we had in the radioactive decay, and that's just called a cooling constant. That cooling constant is going to depend on a lot of things. It will depend on the object itself. It will depend on the surrounding temperature. It will depend on the material that it's made out of, and so the cooling constant is going to be different for every problem. So let's look at a particular example here. We have boiling water that's placed into an insulated cup, which is going to slow its cooling, of course, in a room with a temperature of 20 degrees Celsius. 5 minutes later, after that 100-degree temperature is placed into the cup, the temperature of the water is now 80 degrees Celsius. We want to know then how long it's going to take the water to cool to 60 degrees Celsius. Now, we may think that it took 5 minutes to drop 20 degrees, so it's going to take another 5 minutes to drop another 20 degrees. But that's not the case, because as the temperature of the water cools, the temperature is getting closer to the surrounding temperature, and so it's not going to cool quite as fast. So, like we've done in some of the previous examples, we first want to find our cooling constant, so we'll just plug in the things that we know. We know that after 5 minutes that we have after 5 minutes, we have a temperature of 80 degrees. The surrounding temperature is 20, so we'll plug that in those two places, and the initial temperature was 100. And it's just a matter now of solving for K. So we'll go through the same type of steps that we've done in the previous problems, and we get K is equal to the negative natural log of 60 over 80 divided by 5. Again, we can simplify that 60 over 80 if we want. It's not necessary, but we could if we want. Then what we'll do is we will take the particular situation that we're looking for. In this case, we want a final temperature of 60 degrees Celsius, and we'll plug that into the formula. So we want a final temperature of 60, and we want to solve for T, and we plug in all of the appropriate information in here. Notice also that we plugged our K value in right there. Also, notice that in our exponent we have a negative times a negative. We'll get rid of those just to simplify things and make the process of solving for T easier. So we'll divide by 80 on both sides. We'll take the natural log of both sides, and we can divide by the natural log of 60 over 80 divided by 5, and we get our final answer for T, which is going to be 12.047 minutes. It's important to notice here that this 12.047 is not 12 minutes after the 5 minutes, but it's after our initial time. It wouldn't hurt to note this here, but it's when T equals 12.047, which is not 12 minutes after it was 80 degrees. So it's going to take approximately 7 more minutes for it to cool another 20 degrees. We'll see the same type of thing if we wanted to see how long it would take to cool to 40 or all the way to 20, which actually by this equation it would never actually get to 20. It's always going to stay above 20, but it will approach 20 as time goes on forever. These were a few applications of exponential growth. There are many, many more. You can look at some applications in your textbook, or you can find some really in any calculus textbook or science textbook for that matter.